Hello and welcome back to the Oxford Online Maths Club. My name's James and we've got another episode of the Maths Club today dealing with a topic I'm calling Divide and Conquer. To be honest, I just wanted to put that in the thumbnail with the cross swords and the division symbol. I thought that would be fun. Hi to people watching. Hi if you're joining us for the first time or if you've been here before. If you've joined before, maybe you already know how to find the live chat feature. If you're new, it's over at slido.com. That's slido.com/OOMC, which is the name of the show, Oxford Online Maths Club. That's where you can tell us stuff live during the episode if you want to get involved. And it's also where we run the poll for how was your day, which I like to do at the start of each episode. So how was your day on a scale from 1 to 5? Quick scheduling update. So you might be joining us expecting a computer science takeover. We advertised a computer science takeover at one point for today's stream. It's going to be computer scientists taking over and taking my square and talking about computer science. But I have quashed the rebellion. No, wait, that's not quite right. I have resisted the coup. I have undone the takeover. No. There's a scheduling change, and this week it's me, and we're scheduling a CS takeover for a different week. So we will get some computer science. I've listened to the sound of the baying mob though coming for the show, and I'm talking about a kind of topic with some overlap to computer science today. I'm talking about an algorithm that I'd like to show you. People in chat are mostly having quite a good day today. I think I'm having a 4-star day. I just met some students to talk about, we did some tutorials on the second year maths, this particular topic that I've been doing with them. It's the topic, if you saw the episode with the route for a car to take, as it tried to get in the fast lane and then get back out of the fast lane. I mentioned there's some maths for that. We did a tutorial on that for the second years today. Anna with 2 exclamation marks. That is a great username. Anna with 2 exclamation marks is first time watching live. Hello, good to see you. I want to pick up on something from the factorization live stream. Something that sort of I was doing in the wrong order, but we're going to pick up on something from there. My choice of algorithm is inspired by that particular episode. Right, okay, we've ended up on 3.9, which is not a fantastic hive mind score. See if we can get those numbers up. Doing some maths. And just talks about the open day. We had an open day last weekend and the weekend before. Last weekend I had some computer scientists join me on a panel with students and staff. If you want to see that, it's on this YouTube channel. If you missed the open day and you'd like to come to a different in-person open day, we're doing more. We do quite a lot of open days around here. The next ones are at the end of June, so at time of recording, that's a month or 2 away. No booking required. Thousands of people just turn up in Oxford, and all of the colleges are open, all the departments are open. There's a couple of maths talks, not that many. Mostly people are not many maths talks in the department. Mostly people do stuff in the colleges that day. So hi, who else is here? Hi, I can see Maya's here, and Burrito Man, of course. I as well. Brilliant, good. Okay, so. During the factorization live stream, I got to the bit at the end where I suggested that finding highest common factor is not as hard as factorizing the numbers. And this made sense to me because I know this one particular algorithm for doing that. But it's clear that some people in chat haven't seen the algorithm. So here's something that I want to do, I think today on this episode. I'd like to try and explain Euclid's algorithm. Addition Euclid, and the tagline here is to find the highest common factor without factorizing. So maybe you've got 2 numbers like 1998. Yes, I do have a bit of paper just off screen with the numbers on, and 629. And the question might be, do these numbers have any factors in common. And I guess, what's the highest common factor? And I just saw in chat, yes, we do have a new moderator today. Rory is moderating chat. I said hi to Rory earlier, if you would like to see how to spell Rory. Rory is also, I think, replying to some people in chat. If you see Rory, say hi to Rory. Right, I don't know if they're watching live, so they are possibly going to get a sudden influx of people talking to them. Morgan's here from the online open day. Hello, Morgan. Brilliant stuff. Okay, there we go. Good. Okay, so on the face of it, this question looks really hard. It looks like we might have to factorize both of the numbers. They don't have any obvious factors. Except, sorry, they do. One of them has one obvious factor. It's the left one. It is an even number. I know a factor about those. I guess I know 2 tricks. Maybe you know more than me. I know if it ends in an even number, it's an even number. And I know that if it ends in a 5 or a 0, then it's a multiple of 5. And I guess those tricks combine into the multiple of 10 rule, which if it ends in a 0, it's a multiple of 10. I think other people know some rules about 3 and maybe 9 and maybe a divisibility test for 11. I think there's one out there. And there's maybe something very complicated you do for 7. Let me know in chat if you know what I'm talking about for clever ways to check if numbers are multiples of 3 or 9 or 11 or 7 or something. Anyway, I don't want to do those kind of like bespoke special methods because, as you know, there's infinitely many primes, so just checking for special tricks for each prime, it's not what I want to do. Hey, I've looked at parts about Rory. There we go. Yeah, okay. So I want to try and avoid using these kind of clever tricks, if possible. Maybe someone in chat is really good at checking prime numbers, right? We talked a little bit about factorizing numbers, how if you're very good at factorizing numbers, then you've already worked out all of their prime factors. I suppose maybe once you know all the prime factors, it's not so hard to work out what the highest common factor would be. You would look at which primes they've got in common. And with factorizing. So if you're willing to go and factorize both numbers, then I guess we'll do like 2, 9, 9, 9. You'd make that kind of factor tree, right? Is it 9, 9, 9 there? So then 3, and then 3, 3, 3, I guess. And then 3. I should have used my trick to spot that was a multiple of 9. And then 1, 1, 1. You've got to keep breaking it down. And we're doing a lot of work. I've now got to think really hard about the number 1, 1, 1. I suppose that's also a multiple of 3. Oh, this is great. I'm having a wonderful time. Okay, so breaking it down into these steps. Turns out I actually enjoy doing that. I didn't know that about myself. But it's work, it's effort. And I've also got to engage with number 629, which is not so nice. Yes, people know about 3, right? Nobody likes 7. Adding up the digits. Yeah, brilliant stuff. Okay. Yeah. Anusha is here. Then it's about adding. Yep. If you add up the digits, that's sometimes called the digital root. ROOT, root, digital root. Not to be confused with square root, I guess. If you calculate that, then the number itself is a multiple of 3, if and only if its digital root is a multiple of 3. Good. Can Euclid's method also find the lowest common multiple? Yes, I think so. I think you've got to do something else at the end. You've got to work, right? There's a relationship between highest common factor and lowest common multiple that if I really think about, I can derive. But I'm going to delegate that to you. I'm going to get you to think about the relationship between highest common factor and lowest common multiple for me. Okay, right. In terms of primes, okay, you think about that. I'll explain Euclid's algorithm. The way it works is like this. These numbers are really big, so my aim is to work with smaller numbers. I'm really sorry if you can hear lots of building site noise in the background. Tomorrow is some sort of top of the building ceremony that I don't think means they stop building the building, but they announce they've reached the sort of maximum value of the thing. There was a similar ceremony for the minimum of the building when they had finished digging the hole that the building's in. So, you know, it's good to celebrate the extreme values, I guess, minimum and maximum. Okay, so I'm going to try and make some smaller values. First idea, if 1998 and 629 have a common factor, have a factor in common, then that is also a factor of, and then I'm going to do the difference. That'll give me a smaller number, hope you agree. Smaller than 1998 anyway. That'll give me a smaller number, and if there was a factor in common there, the first one's a multiple of, I don't know, 7 maybe, and the second one's also a multiple of 7, say, then the difference will also be a multiple of 7. So we'll have a smaller number to look at, smaller than 1998, that still has the common factor information built into it. So there's something slightly technical to check there, that if these two numbers are both a multiple of something, then they're differences as well. It's not impossible to check. And also, and this is more subtle, but if something's a factor of that difference, and it's a factor of 629, then it would be a factor of 1998. So this new thing is not the highest common factor on its own, but if I look at it and the number 629, or I could pick 1998, but if I look at one of those and the new thing, I can replace my original problem with these two big numbers with this new problem with smaller numbers, the difference and one of them. And it's an if and only if situation, that a common factor of these two new numbers would also be a factor of the other one. I'm being a little bit vague about which one I should use. I should be more precise for my algorithm, shouldn't I? Yes, here we go. Yeah, so this is always true. Let's do the proof. That's Andre's put a proof in chat. So let's generalize this. If A and B, am I using different letters from you? Maybe. If A and B are both multiples of D, then, well, what would that mean? That would mean that A is some multiple of D, using whole numbers, and also B is some multiple of D, where I'm just picking random letters of the alphabet here. I guess M for multiple and K for some integer. Okay. And then, sorry, my sentence has gone all the way over onto a third line now. Then A minus B would be a tiny bit of algebra, also a multiple of D. Verbs are important. Also a multiple of D. There it is, it's something multiplied by D. And this comes from a school of thought where whenever you see the phrase factor or divisor, you can write down a bit of algebra for what that means. Whenever you see the word factor, that means some algebraic relationship between the numbers, possibly with some variable in there hidden away, like what do you multiply by, what I've made explicit by calling them K and M, but quite often the words have particular algebraic meanings. Anyway, I'm getting away from my point, I suppose, which is that you can actually work out what this number is. Goodness me, that was a rhetorical comment that I slightly regret because now I have to do some subtraction. Not that there's anything wrong with subtraction, just there we go. 1369, I think. Chat will correct me gleefully if I've subtracted wrong. And then repeat. So I guess my idea is to work with 1369 and 629 instead. Okay, so that's the first idea, and in fact this is good enough. the only thing I had to do there was subtraction, and that was stressful for me because it was a 4-digit number and I'm on camera at the moment. But if you're doing this at home and you're not on a live stream, then doing the subtraction is orders of magnitude easier than dividing by primes or something, or doing this trial division stuff, or factorizing. Subtraction is kind of easy. Even better, if you give this to your computer, then subtracting is really easy. So yeah, it's what Maya says in chat at the top here. You just keep going. That's it. It's the first idea, and sort of also the last idea, that you can keep going. So next I would do the difference between these numbers, and I would keep working out the difference and keep getting smaller numbers. Bit of maths there to check that they keep getting smaller. Until eventually, I suppose I'll be left with, what will I be left with? I suppose two numbers that are the same. One will be a multiple of the other. And at that point, I can start looking backwards and say, aha, I think I found the highest common factor now. So, I do have a second idea. I do have a second idea to make this slightly faster. The stream's called Divide and Conquer, which is to do a little bit of division. Second idea is to speed that up with division. Now, I'm working with whole numbers, and the thing about whole numbers is that you can't just divide a whole number by another whole number and expect to get a whole number back again. That sounds stupid when you say it out loud, but in some sense the whole numbers don't support division like that. 1998 divided by 69 is not a whole number as far as I can tell. But there is this thing you can do, right? You can do division with a remainder. So thinking about division with remainders. I'm not sure what order you learn this in at school. It's possible that you learn about division with remainders before you learn about dividing whole numbers to make fractions. I'm not really sure. I mean, for me it's a long time ago. For you it's, I guess, also a long time ago. Which did you learn about first? Remainders or fractions? I would like to talk about remainders today rather than fractions. Yeah, and there's some good questions. An anonymous person has asked whether we're going to find the highest common factor or just a factor, which I would like to prove. I'll have a line of equations to show you in a moment. Andre says, does it matter which number we keep? No, I would keep the two smallest numbers if you're doing repeated subtraction. We're going to see that the division idea with remainders speeds this up a little bit. So that instead of repeatedly subtracting 629, I'm going to skip some of these numbers. Anyway, okay. People are telling me about remainders. Oh yeah, remainders first. Okay, so we're going back to remainders. Okay, maybe you can remember how remainders work better than me. Here is, I think, a true fact, which involves remainders, which I have on a bit of paper. So if you try to divide 1998 by 629, I think you get 3 and a bit. 3 with a remainder. With remainder 111. I've seen that number recently. Which is just another way of saying, by the way, that if you subtract 629 again and again and again, you'll get down to 111. At which point you can't subtract 629 anymore. Something different is going to happen next. So if you prefer to think about repeated subtraction, which is something I can do by hand quite easily, then maybe this line says something like, what will happen as you keep doing that repeated subtraction? Subtracting the same number until you can't. And if you remember how remainders work, then maybe you have some sort of method in mind for how you would work out, I suppose, this number, 3, for the quotient, and this number, 111, for the remainder. Okay, your computer is quite good at this calculation as well. If you know some programming language, like, I don't know, choose your favorite, but you maybe know an operation that's called something like mod or percent symbol or something like that, depending on which language you speak. This is my nod towards any computer scientists who have turned up because of the advertised computer science takeover. Look, I put a percent symbol on for modular arithmetic. That was for you. Okay, I'm going to erase it. Anyway, there's a way to get a computer to work out these numbers quite quickly. And I only really care about the remainder. Of course, I care about the remainder. The quotient for how many times you would have had to do subtraction, fine. But the remainder there. Yes. Anybody who talks to snakes, speaking parcel tongue, or as Python, as people sometimes call it, use percent for their remainders. Well, that's what chat tells me anyway. Even mod supremacy, right? Okay. Okay. So I think our plan was to keep going. We might have got to a point where we can't subtract 629 anymore, but we're not done. We're now looking at the question as to whether 629 and 111 themselves have any common factors. Because, just to say it again, if this is a multiple of d on the left, ooh, I haven't got cursors on. 2 seconds, I'm pointing at stuff that you can't see. I think I've enabled it. Hey, there we go. What's that? You can have some. I think I turned it off for the open thing. Sorry. If this is a multiple of d, hey, there we go. And if this is a multiple of d, then the remainder has to be a multiple of d as well, because it's just left-hand side subtract this thing with a 3. If those are both a multiple of d, then so is this. So we haven't lost our highest common factor, it's still in there somewhere. Okay, so we can do this again. So I'm going to bring these numbers down. 629, I'm going to put that in the driving seat. And I'm going to bring down 111. But I'm going to ask the same question for what happens if you, I guess, repeatedly do subtraction on these numbers as well. Because if they've got a common factor, then when I do the difference, that will also have the same, that will also share that common factor. And if you do them one at a time, you have to do, how many is it? About 5? Not as many as 6, because that would be 666, which is too large. So I think about 5 times that. That would be 555, and the remainder is 74. Okay, so now we've changed our original problem to say, do these numbers have a common factor? I think now we're interested in whether these numbers have a common factor, 111 and 74. And now the numbers are getting smaller. Now I might stand a chance of factorising them, but I'm on a roll, so I'm going to keep going. So what do? I don't really care about the 5, that's how many subtractions you had to do, that's how long you were pressing equals on your calculator, but I do care about this number 111. If there's some sort of hidden gold of that common factor, then it's in this number and that number to start off with, and it's also in 111, so I'm going to keep looking at 111, I'll bring that over here. And I'll look at 74. And 111 is, I think, 1 times 74 plus 37, and one more go round. 74 is 2 times 37, and then something interesting happens. If you repeatedly subtract 37, you end up at 0. So I could put plus 0 here. So here's the claim for Euclid's algorithm, and what's on screen now is Euclid's algorithm. Here's the claim. The last number you were considering in these lines of repeatedly doing modular arithmetic, repeatedly doing, the quotient and remainder calculations for doing the division, the last number you were looking at, in this case 37, I guess that's the final non-zero remainder, because it's come from there. The final non-zero remainder is the highest common factor. Let's write that on the board. Hi, you've just joined. Yeah, this is a continuation from, I think it was 2 weeks ago. We talked about factorising, and I mentioned something called Euclid's algorithm, which I now try to explain in more detail. The last non-zero remainder is the highest common factor. So what I've been trying to convince you along the way as we work down the page is that we aren't losing anything. There isn't a bigger common factor. If there were a bigger common factor, then it would be a multiple of 1998, it would be a multiple of, sorry, it would be a factor of 1998, it would be a factor of 69. This kind of imagined highest common factor would be a factor of 111, it would be a factor of 74, it would be a factor of 37. So it's got at most 37. So there can't be a higher common factor. A higher common factor would have to be a factor of 37, and you can't have a larger number being a factor of 37. So that's a kind of upper bound. The new thing that I'm claiming, here we are, yeah. The new thing that I'm claiming is that this number we've got to now is actually a factor. That wasn't true up here. 111 is not a factor of either of the things that we had before. 74 is not a factor of 111. I mean, that's even and that's odd. But 37, I claim, is a factor of all of the other important numbers on the board, all the ones in this column and in this column and in that column. So the last thing I need to prove highest because, and then working down the page, any factor. Sorry, just writing out what I said. Any factor must divide 37. And I suppose the last thing I need to convince you is that it actually is a factor. Oops. Because, and now I need to read up the page to convince you that, well, if 37 divides itself, because there's a 0 right at the end here, there's nothing over there. Because there's a 0 over here, 37 is a factor of the thing on the left. It's the first time this is true, that the number we've got is a factor working backward, but working back up again, 37 is a factor of this. And then once you've got there, once you've agreed that, oh, this last non-zero remainder has to be a factor of the previous thing, because the last line I write will be number is multiple of that plus 0. That's what it means to be a factor. Once you've agreed with me that the last non-zero remainder is a factor of the previous remainder, now you can work up the page, because each line says that this thing is the sum of two things. And as you work upwards, we can go one line at a time. 37 is a multiple of 37. I think I just convinced you that 74 is a multiple of 37 down here. So therefore this stuff is all a multiple of 37, and that's called 111. And now go up a line. I think I convinced you that 74 is a multiple of 37, and I think I just convinced you that 111 is a multiple of 37. So therefore this combination is also a multiple of 37, and keep working up. We can work upwards from the end. That is not a mathematical proof that I've written on the board, but I have run out of space. The best excuse for not developing your proof on page. Yep, 37 divides all of, should I put colour around them? All of these numbers. I've been mentioning them as the kind of important numbers, or the ones we consider as things containing that highest common factor. 37 divides all of the things in those blue columns, which means it divides the original numbers. And reading down the page, anything that divided those divides each other thing in the blue columns. So it has to divide 37. So this is really nice. This shows that this is actually the highest common factor at the end. We didn't have to factorize either of the numbers. Brilliant. Okay, I think that was a good use of half an hour. A couple of weeks ago I tried to do this in about 3 minutes and that was not good. Good. Okay. It is much nicer. Yeah. 37 37 divides all of the remainders. And people in chat talking about Bezout identity, which I think I'll put in the further reading this time round. There's a kind of thing people normally do next. In fact, when we do this on a summer school, the next thing we do is Bezout's identity, which helps you solve equations using whole numbers. So it's pretty good. But I think I want to pause for a moment and talk about things in chat. 37 is a factor of 0. Yes, 37 is a factor of 0 because you can multiply 37 by a number and get 0. The number is 0. What's a number? A whole number? Lots of things are factors of 0. Yeah, most things. Shriz says this is nicer than doing prime factor decomposition. And yes, there's an anonymous person. Where are they? Down here. So if you're interested in finding out what Bezout's identity, the idea is that you can solve equations like this using whole numbers for x and y. Equations like this, sorry, highlighting in chat. Can I kind of highlight this? There we go. There you go, you get highlighted at the top there. Yeah. So if you'd like to be able to solve equations like that with two massive numbers, x and y, and a plus symbol in the middle, equal to on the right hand side. In this case it says 37. You can imagine other cases with other numbers if you'd like to solve things like this. May have bought myself some wiggle room that I didn't need on the factors of 0. I think 0 is a factor of 0 as well. That was the one I was worried about. Nope, 0 is a factor of 0 because I can multiply 0 by 0 to get 0. Yeah, cool, good. Just wait for it to come in. Anisha says infinity, but then correctly says that's not a number. So yeah, also my cat is not a factor of 0 because it's not a number and because I don't have a cat. Right, good. Okay. We've gone weird. Yeah, good. So if you were coding this up on a computer, what would you do? You'd have two numbers coming in, and you would want to calculate this remainder, which is maybe something like a mod b, mod a comma b, or a% b, or something, depending on your language. And then you'd want to do it again. And there are different ways you might do that. You might write out a kind of for loop to give the computer the instruction to kind of keep doing that. Maybe some sort of while loop if your language has those, to keep going until it gets down to 0. Or you might do some sort of recursion. You might give your overall function or machine for calculating highest common factor a name, and you might get it to call itself midway through. So it would do some calculation to find the number 111, and then it would call the function itself again using the second number and this new thing 111. And which of those is better depends on how you feel about coding them, and probably depends on the language a little bit as well. Who knows, maybe they all work out to be the same thing. So something you might wonder as you're coding this up for your computer is whether or not it's going to stop. Because sometimes you give your computer a calculation to do, like please keep adding 1 to this number until you get to -3, and it just keeps going forever. It never hits this kind of stop condition. So down here, stop. Oh, I'm in baby blue. Let's go to stop. A bit more forceful. There you go. Oh no, chat is now obviously arguing about whether 0 is a factor of 0. Oh no. I kind of had this argument with myself in my head and then stupidly did it out loud with you. Here we are. Here we are. Oh no. Shall I ban 0? Shall we only look at strictly positive numbers? Would that make people feel better? Probably. Yeah. But I don't want people calling like, what's the highest common factor of 1998 and 0? I don't know about that. Maybe I do. Maybe that's stop condition. Return your largest non-zero number. Anyway, here we go. Yep. Yep. People are now talking about indeterminate things when you divide by 0. I think I'm multiplying by 0. Oh dear. And there's a good reminder coming through moderation at the moment. The stream only has 2 rules. Please don't swear or divide by 0. Good. And yes, someone heard about my will it stop question. Yeah, it'll stop because the numbers get smaller. Is it clear that they're getting smaller? Yeah, I think that is kind of obvious that they're getting smaller, right? Because each time, well, really we're doing some repeated subtraction. When you subtract from a number, it gets smaller. Welcome to the Oxford Online Maths Club. Good, yes. This is an important concept because if the numbers aren't getting smaller, then what are we doing? We're replacing our problem with a sort of equivalent problem that's the same size. And maybe we're just going around in circles. This is the idea that we're actually making progress towards solving our problem. So that's nice. Okay. So that'll stop after, well, I suppose the natural question is like, what's the worst case scenario? Does anyone want to have a go at that? What's the worst case scenario for my computer? In terms of, maybe if I imagine that each line takes it a second or something. It's really good at doing this kind of quotient remainder thing. It can do a single line of this in 1 second. There's this kind of worst case scenario that we should talk about, which people might already know in chat. So I'll let you talk about it in chat a little bit. Good question, Maya. Someone replied to this as well. Maya's asked about using this algorithm for fractions, and the algorithm is quite disappointing for fractions because with fractions you can divide with no remainders. You give it 1998 and 69, and it will put in a quotient over here that's 1998 over 69 with no remainder. The fractions, non-zero fractions, from rules of the stream, don't divide by 0. Non-zero fractions do support division quite nicely, and then you never get any remainders, so there's kind of nothing going on there. It's a bit sad. Yeah, okay, let's try some of these in chat. Oh, this is good, this is good. There's some suggestions for what might be bad. Ooh. Anna's question is really good. I will remember to come back to that, but I want to talk about some of these ones. So, people in chat say that worst case if each quotient remainder takes 1 second. There's a suggestion in chat that if their common factor is 1, then things are pretty slow. I guess people are imagining there that if they have a really large common factor, then the numbers that you started with look scary, but actually they were not too bad at all. You know, they'll just stop when it hits that common factor, having got smaller. There is something slightly interesting though, which is that if the numbers are very close together, so suggestion from anonymous person n and n plus 1, so I have something like 90 and 89. So yes, this is pretty bad. And this line, which looks stupid on the board, but would take my computer 1 second, let's say, if each line takes 1 second. But then it does quite well on the next line, look. because next time round it asks for the quotient when you divide 89 by 1, which is, oh brilliant, it's 89, with no remainder. Stop. So it can do this one in 2 seconds, which is actually quite a bit better than the one we were just looking at. Okay, these are smaller numbers, but it's sort of surprising that in this second step look, although the number 89 is pretty large, it's got this huge quotient here, which lets it jump straight down to 0 really quickly. And this is a case where the highest common factor is 1, and it was pretty quick. I suppose also, if the numbers are very different, if the numbers are very far apart, then the very first line you get, the remainder is going to be smaller than the small number. So if you have very far apart numbers, you get quite a lot of work done in that very first line, so it's sort of super efficient in 1 second. So the thing I'd like you to imagine for a worst case is, in this world where one line only takes a second, the worst case would be if that's not very many subtractions. So for example, this line is very good compared to subtraction, I suppose, because this quotient is huge, and it means we get all the way down from 69 down to a lovely number like 74 in that line. So large quotients, that's a line which gets us lots of progress. Over here, these numbers are all kind of about the same size. The quotient is just 1. In here, there's loads of progress made in that line. So if each line takes 1 second, then this was really good, and this was really bad. Yeah, good question. Next, that maximizes this. So in some sense, the worst case scenario, and I'm not being very precise on what I mean by that worst case analysis, but it's pretty bad if the highest common factor is 1 and also each quotient is 1 along the way. That would be pretty bad. Yeah, so we had there, well, the difference between the numbers is very large. So if you start with like 1,000,000 and 10, then I suppose obviously those have common factor 10. If you start with 1,000,001 and 10, then the remainder is at most 10. So the very next line will have small numbers in. This is sort of the perfect balance in a way. The numbers we're going to see in a second, the kind of perfect balance between being too close together and too far apart, where it's sort of awfully bad in the middle. I'm going to work backwards. So my last line will be something like 1 and 2 or something, for really small numbers right at the end. And those will have come from something like this, where now I'll make each quotient along the way 1. So for example, 3 and 2, stupid question I suppose, what's the highest common factor of 3 and 2? Obviously 1, but our algorithm is quite slow to work that out. It tries to subtract 2 repeatedly. You can only subtract 2 once with remainder 1, and then it notices that 2 and 1 have, well, 2 is a multiple of 1. Okay, let's work backwards a little bit to see what's going on here. So these would have come from being the remainder and this number from the previous line. If this quotient is also 1, then I have the number 5 here. And if I keep working backwards to work out what these terrible numbers are, look. So here's an example where the numbers are still 1-digit numbers, 8 and 5, which again obviously don't have any common factor, or have 1 as the highest common factor. But if you do this repeated quotient stuff, it takes so long to work that out using this method, because you would go 8 is 1 times 5 plus remainder 3, and then 5 is 1 times 3 plus remainder 2, and 3 is 1 times 2 plus remainder 1, and then you get 2 as 2 times 1 and done. and it kind of keeps going. These are the numbers that are really slow. If you see a pair of numbers like this, so if I keep working these out, things like this, 13 and 8. And maybe you've seen these numbers before. These are the Fibonacci numbers. So surprise, by the way, Fibonacci numbers, which you might have seen before in some sort of rabbit problem from the last season of Maths Club, where the rule for the Fibonacci numbers is you start with 1 and 1, and then you add together the previous two numbers. That's kind of what I've done here. I've got 2 and then 3 and then 5 and then 8 and 13 by adding together the previous two. Those numbers, consecutive Fibonacci numbers, surprise, have highest common factor 1. So let's put that on the board. Consecutive Fibonacci numbers. I can never spell Fibonacci. Let's just go for it. Consecutive Fibonacci numbers have highest common factor 1 after lots of work. That's kind of the worst case scenario. Okay, bit of fib. Does the number in column 2 have to be 1? No. I'm suggesting that this would be quite bad news for our computer if the numbers were such that this thing was 1. Because then, even though the numbers are small, it's taking loads of lines. If you like, this is how you get 5 lines of work with the smallest possible numbers involved. I could change these to be anything I like and still have some valid calculations on the board. But if I want to show you an example with lots of lines and small numbers, then I should make these things the number 1. Up here is examples where like the quotients were larger numbers and things happened much faster, including this example we started with, where we started with a 4-digit number and we got down like 4 rows. That was fine. If these had been consecutive Fibonacci numbers, we'd be, we might still be going. Yeah, so 2 times 8 plus 5 would, down the bottom here, would be, I suppose that's the number 16 and 5 is 21. And that would take the same number of lines as this. If you were looking for the highest common factor of 21 and 8, which again, still, you'd think that would be really easy, but oh no, using this method, it's really slow. 21 and 8, yeah. The reason I put 1 here is just to show you an example with really small numbers. In some sense, big numbers probably take longer, because just doing anything with large numbers takes longer. So the kind of interesting worst case is an example that is both slow and uses small numbers. Right, so three numbers, and I saw this question before and said I'd come back to it. What do you do if you want to find the highest common factor of 3 numbers all at once? Let's talk about it. So let's say you've got 3 things. What should I do? Maybe 1998, 629, and 3,700. Suspicious. And you want to see if they've got any highest common factor shared between all 3 of them. So I guess what you could do is you could run the algorithm to find out whether these ones have got any highest common factor, and it turns out they do. And then you could run the algorithm on these ones to find out that they've got highest common factor 74. And then you could run it again on those highest common factors to look for the kind of ultimate highest common factor shared between all of the numbers. I guess that's like organising a tournament. Like if you had 4 of them, it would look more like a tournament, right? You would play off the pairs to find, hey, have you got any common factors? Have you got any common factors? Okay, now let's look for the real common factor shared between everyone. Bring me your highest common factors each. Okay, now compare. So you could kind of funnel them through in a stage. But separately, you could adapt the underlying idea if you wanted to. If you felt this was a little bit inefficient or ugly, you could adapt the original idea by taking two of your numbers, taking the difference, and replacing whatever your largest number was with that difference. Because anything that's shared between all three of these will also be shared with any random difference that you take between two of them. And I'm not sure, there might be some scenario where that's a better idea, like a genuinely faster algorithm. I don't know, maybe you've got 1,000 numbers and they're randomly distributed and you would like to check that they don't have a highest common factor, so you start randomly doing subtractions and looking for pairs of them. I'm not sure, but not impossible that there's something like that. Yeah, difference between all three. Yeah, you could. Yeah, I'd say that suggestion in chat from an anonymous person is the thing that I'm mentioning. That this kind of first principles approach, just sort of start again, but do differences on them. Good. Okay. I did see someone was being very upset about the map in chat, which I thought I'd mention on stream. Sorry about the map. Good. Okay. Yeah, Anisha. Now that I'm thinking about it like a tournament, I guess what I'm suggesting that you do is you clone 3700, put it over here, and then run the tournament like this. Winner at the end. Which makes it feel like I'm missing a trick, because I've made it into a kind of bracket tournament thing like this. Can I explain again why the remainder must have the same highest common factor as the original two numbers? Yeah, sure. So there's this up and down argument. One way I would like to read the lines top to bottom, and the other way around I would like to read the lines bottom to top. So, reading from the bottom, the cool thing is that we finished with a 0, which means that our last line reads, thing here is some multiple of the thing here. So good news, this last thing that we had genuinely is a factor of that thing on the left there. Probably I should give them all names and I should refer to them by name. I'm being lazy, and I'm going to point. I've enabled the mouse, now I will point. So this last line is different and interesting. It says that something is genuinely a factor of something else, and now work up the page. So once you've decided that these two things are genuinely multiples of this last circled number, start working up the page. If those things are both multiples of that, then aha, so is this thing on the left, because it's a combination of them. This is, I don't know, quotient times k times the number, and that is the number. So they're both multiples. And now, kind of by induction, I suppose, keep working up the rows. The things on the right are both multiples of this number, so is the thing on the left. And if you keep going up, eventually you'll hit your top line, which had the original numbers in. So they're both multiples of this thing. This is a common factor. Is it the highest common factor? Well, suppose there's a bigger factor. The bigger factor would be a factor of the starting numbers, and therefore it would also be a factor of the remainder. And now work down the lines. So as well as being a factor of the remainder, when we look at the next line down, well, here's something we were already thinking about, and here's something else we were already thinking about. It would also be a factor of this remainder, because everything else is a multiple of this supposed higher common factor. As you keep working down, eventually you'll bump into the last non-zero remainder, and you will say to yourself, well, that would be a multiple of this higher common factor. But you can't be a multiple of something that's higher than yourself. So contradiction, there isn't a higher common factor. So it's reading the lines in two different directions, reading them bottom to top to convince yourself that this is genuinely a factor of the original numbers, and reading them top to bottom to convince yourself that there isn't a higher common factor. It's not a stupid question as to whether this works with negative numbers. And Nusha, this works brilliantly with negative numbers. It works just the way you want it to. I've even got a trick for you where you don't have to take the remainder to be a positive number. You can go one step more and then have your remainder be a negative number, and nothing actually goes wrong. It's great. So for example, here, if I'd been allowed to write 6 times 111 minus, the minus would have been 37, and I would then be done. So if you're allowed to look at negative numbers as well, to, I suppose, look at the kind of closest multiple, then you would save yourself some lines. It works really well in negative numbers. Klaxon, chat has mentioned complex numbers. I've got a thing for this. I'm so glad you did this with 5 minutes to go. You can do this with complex numbers and nothing goes wrong. Here's a Desmos that I built. I'm so glad you mentioned complex numbers, chat, well done. So if you've got 2 complex numbers, the challenge is that, well, we can do the same sort of division. We could do this quotient and remainder business. I'll show you how in a moment. We might worry that, well, are we making progress? Are the numbers getting smaller as we do this remainder and division thing? Because complex numbers don't have inequalities. The numbers, you can't say that the number is smaller than the previous number. That just doesn't mean anything for complex numbers. But luckily, there is a concept of whether the number is close to the origin or not. So in the Argand diagram on the board here, the x-axis is supposed to be the real part and the y-axis is the imaginary part. So I've got my 2 complex numbers there in the Argand diagram, and the red one is closer to the origin than the green one. And if the components there, real and imaginary parts, if those are both whole numbers, then the distance to the origin is not a whole number, but the distance squared, the kind of Pythagoras a squared plus b squared thing, a squared plus b squared is a whole number. Anyway, technical note aside, you can use that to explain why the algorithm is going to terminate. That's the thing that gets smaller. That's the measure of progress that you can use line to line. Let me show you what the division looks like, because you know how to divide numbers, I think, and you know how to do this quotient and remainder. The thing that you would do is to find a multiple of that number that's pretty nearby. Like we had a 629 and 111. You can kind of see there's about 5 or 6 where you should look. 5 is too small, 6 is too large. That's a very inequality way of thinking about things. 5 and 6 are both pretty close by. So what we would want to do here for the division algorithm, Euclid's algorithm, is to find a multiple of this point, this red point, to find a multiple of this point that's pretty near the green point. Let me show you the multiples of the red point. And I'm showing you the multiples where I'm multiplying that complex number by some other complex number with whole number components. These are called Gaussian integers, by the way, after the mathematician Gauss. Complex numbers where the real and imaginary parts are both whole numbers. So if you take all of the multiples of that one, including the complex multiples with integer parts, you get this grid, which looks random the first time you see it, and then your eyes focus and you see there's a pattern there. So reading out this way, I've got 1 times my number, and then going out this way 2 times this number, 3 times the number, 4, 5. I'm going out like multiplying a vector by a scalar, going out in that direction. And I've also got, going over here, I times the number that I started with, which is giving me a rotation by 90 degrees over here. And I've got 2i times the number over here, and I've got this kind of square grid of multiples. This is what multiples of a fixed number look like in the Argand diagram using Gaussian integers where the real and imaginary parts, both whole numbers. I think it's really nice. I mean, it squares on its side, right? Anyway, the way you would do the division algorithm is to take one of these points that's near to the large number. So large in the sense that's far from the origin. I've got this green point that's like my large number, like 1998, but I think in this case it's actually, what is that? 8 plus 10i. Anyway, large number. Find one of these blue points nearby. They're not that far apart because the box of the square has got a particular side length. Take the closest one. Maybe that one, looks quite good. And then my remainder is the difference. And because I need a tiny bit of geometry here, because every point inside a square is within one side length of some corner of that square. The distance, the kind of the remainder turns out to be a number that's closer to the origin than the thing I started with than the red point as well. So you can do this kind of thing using distance squared, as your measure of whether numbers are large or not, and everything works just fine. Actually, it's really nice that we did the positive-negative thing, because the positive-negative thing helps you to realise that you don't have to round down when you do the quotient. You can round up, and here we're rounding to one of these nearby 4 points. And then my remainder will be maybe some really small complex number like this, and then I'll do it again. So my remainder looks like it might be, well, if I use these points, just the number 3. So then I'll do it again. I will move, so to move the points, I've got to move this one to 4 plus 3i, and I've got to move the red one down to the number 3. So now I would look at this remainder. Over here it's 1, and the numbers have turned out to be highest common factor 1. Oh dear, right, okay. So you repeat this. It's quite fun playing with this and moving the kind of square grid around to get these different grids of squares. I'll zoom out. Whee! Right, okay, we've hit 6 o'clock. It is the end of another episode of the Maths Club. Hope that was helpful. Halfway through, I think you learnt the Euclidean algorithm, and then we did half an hour of sort of messing around and extending it to complex numbers. Yeah, what do we mean by highest common factor? If there are no inequalities, what does it mean highest? We mean the one that's furthest from the origin, and it's actually not unique, but one of the ones which is joint furthest from the origin, and is a factor of each of those 2 starting numbers. It's a really weird concept. Good, okay. What a nice point to finish on. I think we'll stop there. For 3 numbers, can you, hang on, what's this? For 3 numbers, can you not just work out the difference of 2 and then use that replacement of the 2 numbers and use the algorithm? Maybe. I'm a bit worried that the number you get at the end might not be genuinely a factor of those 2 things that you originally took the difference of. I'm trying to work backwards in my head to see whether it would be a factor of those 2 numbers you started with. I'm worried it might not. Yeah, if I add 1 to each of them, then they might stop being a factor of this thing we finished with, but have the same difference in your algorithm. Good, right, okay. Thanks for watching in live chat or on the recording on YouTube. We're supported, as always, by the Mathematical Institute at Oxford and Jane Street Trading. You can find out more about the Mathematical Institute on our website. There's a link there to find out more about Jane Street as well. We'll be back in 167 hours for another episode of the Oxford Online Maths Club. Until then, have a good evening, have a good week. We'll see you next week. Bye.